Welcome to the online wastewater treatment operator certification training event. I'm Jason Flowers with Geosyntec Consultants, and I'm presenting this on behalf of the Arizona Department of Environmental Quality. This next module, Module 4, is going to cover secondary treatment, which includes traditionally aeration basins and secondary clarifiers. The following diagram is for a conventional activated sludge system. In this system, you have primary effluent or secondary influent that has gone through some preliminary treatment, flows into an aeration basin. The aeration basin is where the wastewater is aerated, and the pollutants are converted into biomass by additional bacteria that are present in the aeration basin. From there, the wastewater and the biomass flow to a secondary clarifier, where the biomass that is generated in the aeration basin is separated out at the bottom of the clarifier, and the clear wastewater, the secondary effluent, then moves on for further treatment, including disinfection. That biomass is then has potentially two paths. Number one is return activated sludge, where that biomass is withdrawn and recycled back to the aeration basin, where it brings back the culture of bacteria into the aeration basin to continue degrading more of the wastewater that comes into the system. That is return activated sludge. In addition, some of the wastewater will be removed from the system as waste activated sludge and be disposed of in your solids handling treatment process, whatever that may be. That removes excess biomass so that the bacteria population in the aeration basin does not overgrow and meets the growth requirements for the performance that's needed for your system. Now, what we showed you was the conventional activated sludge system. There are a few other variations in terms of the process. There are sequencing batch reactors in which the entire process occurs in one tank. In one tank, you'll fill the aeration basin. You'll then react it by adding in turning on the aerators. You'll settle, decant, but remove the wastewater from the same tank, and then have an idle phase. That's all within one system, and that's a sequencing batch reactor. You can also have large oxidation ditches, which are large aeration tanks, effectively, that have a much longer hydraulic residence time and typically longer solids retention time as well, too. These would flow into a clarifier, where a clarifier would be used to capture the solids in addition to that. Membrane bioreactors is a newer and becoming more common replacement for conventional activated sludge systems, which a membrane performs the actual solid separation rather than a clarifier. This allows you to have a higher amount of mixed liquor suspended solids concentration in your aeration basin, because settling is no longer a driver for the performance. And that allows you to have potentially more treatment per cubic foot of volume than would be in a traditional conventional activated sludge system. On a slightly different treatment pathway, there are attached growth processes. These are processes similar to trickling filters or moving bed bioreactors, in which the bacteria grows on a media such as rock, river rock in the case of trickling filters, or artificial media like HDPE, which can be used both in trickling filters or in what we call moving bed biofilm reactors. In this situation, the wastewater flows over or around this media, and the bacteria grows on that surface rather than being suspended. These systems will typically have a clarifier to capture any solids that maybe do leave the system, but overall, the main growth is no longer suspended in the water, but is attached to a media surface. Despite these different variations, we're going to focus on the conventional activated sludge system because many of the concepts are transferable and is, at this point, the most standard way that wastewater treatment systems are configured to the state. What we're going to cover is, number one, how biomass transforms pollutants in the system, what parameters are important for the biomass health to ensure good performance, and also how you separate solids, the biomass, from the wastewater effluent as well, too. So first, let's start off with how biomass transforms pollutants. So how does secondary treatment do the actual transformation, removing pollutants from wastewater? In this case, it's actually the biomass that is the main drivers of it. The biomass, what I mean is microbial populations, which can include many different organisms, whether that's bacteria, you talk about rotifers, ciliate stalks, all sorts of organisms are involved in the process. But when we think about primarily the ones that we focus on we focus on heterotrophs and nitrifiers. These particular bacteria, which are the two key that we mostly focus on, when we think about what they're doing, they're taking carbon source or their food source, which is the wastewater, plus nutrients, which is also present in wastewater, and oxygen that we deliver to them. And they take that as an inputs to them and they produce new biomass. So they're converting all that carbon in the food into new biomass and then some waste products as well, is what they're doing. Now we're going to focus on some of the basic metabolism of what's happening for each of these organisms. So, under aerobic growth, must have dissolved oxygen, and the classification of aerobic growth is where dissolved oxygen is present. And so, under this situation, the heterotrophic bacteria, which are the bacteria that break down BOD, they take these longer carbon chains of molecules like glucose or acetic acid or starches, and they break those down to smaller carbon molecules until they get to carbon dioxide. And through that process, that's where they actually get their energy. That's their mechanism of being able to get enough energy to grow and to make new biomass. Similarly, for nitrification, it is also an aerobic process in which this is a little bit more complex because historically and primarily, this is a two-step process in which a different type of organism than the heterotrophic bacteria will take ammonia and you give them ammonia, give them oxygen, and these bacteria, specifically the first step, which are called ammonia oxidizing bacteria, will take ammonia and convert that to nitrites. In addition to that, the nitrite that's produced from those ammonia oxidizing bacteria will then be fed to nitrite oxidizing bacteria that then, under aerobic conditions, will take the nitrite and convert that to nitrates. These processes do give off some waste products associated with them. One is carbon dioxide, which goes off in the air, very similar to the heterotrophic bacteria, but it also does produce hydrogen ions, which do consume alkalinity as part of the process. And that's going to be something that we're going to be talking about more in terms of impact on the process later on. Now, there are some recent studies that have identified a new bacteria that can just take ammonia to nitrate without requiring that intermediate step of nitrites. Those are called Comomox organisms. And they've been found to be present in wastewater treatment systems, but I'm not certain if the role and how important they are in the process has been defined at this point. Also, in conventional activated sludge systems, there is a way that is not an aerobic process, but an anoxic process in which nitrate can be removed and can be converted to nitrogen gas. This is a particular situation that involves a process called denitrification, which when the bacteria use the oxygen that's present in the nitrate and nitrite instead of using oxygen itself, and through that process, they will remove the oxygen from that and then produce nitrogen gas. This process is used whenever you want to remove total nitrogen from your wastewater. If you happen to have a permit limit for your discharge, in which you need to get nitrogen out of your effluent before it's removed, you'll have anoxic zones in your systems. We'll talk about more about where those are installed and how that works. But one of the benefits of this process, while the nitrification process consumed alkalinity, we are actually producing alkalinity in this situation. So there is a little bit of a balance here that we'll be talking about more later on as well. An important factor to think about this, because there is no aeration that's happening in the anoxic zone, because we do not want to introduce oxygen, because otherwise the bacteria that do denitrification would just use oxygen instead of the nitrate. To keep these organisms in suspension, though, we have to use mixers that keep them mechanically mixed so they're staying suspended. Otherwise, without aeration, without mixing, they would just settle to the bottom. So it's an important factor associated with these environments. Let's put it all together. This is a classic biological nitrogen removal configuration for an activated sludge system called the modified Lützi-Ettinger process. In this scenario, primary effluent enters the aeration basin, where it first flows through the anoxic zone, and stuff happens. We're going to ignore it for now. Then it gets to the aerobic zone. Under the aerobic zone, BOD oxidation happens, so the carbon material gets converted under the aerobic conditions to carbon dioxide, and that biomass grows. In addition, the nitrifying bacteria that are present there will take that ammonia that's present in the primary effluent and will convert that to nitrite. So under this aerobic zone, BOD is oxidized and ammonia is converted to nitrite. From here, then we have a mixed liquor recycle, which is typically between 1 to 4 times the flow of the wastewater coming into the system. We actually recycle that wastewater back to the noxic zone. This wastewater here has no BOD because it's been oxidized, but nitrite is present. So now we're feeding in nitrite under the noxic zone where there's no aeration being fed. And then in the primary effluent, we are bringing in fresh, raw wastewater with lots of BOD. So now we have a great environment for the denitrifiers to operate and where they can then convert the nitrite to nitrogen gas and remove the nitrites. So the next few slides, we're going to talk about the parameters that influence biomass health that you need to think about when operating your systems. When we think about the parameters, we've got 7 primary ones that we're going to focus on that are important for the bacteria to make sure that they are happy and operating well. Number 1 is food or substrate, as we call it. Obviously, bacteria need food to be able to grow, so that's important. Number 2 is oxygen. With the exception of the anoxic zones, oxygen is required for any of the metabolisms that are needed for the wastewater to be treated by the bacteria. Number 3 is nutrients. They're going to need some levels of nitrogen and phosphorus, whether you're doing nitrogen removal or not, or phosphorus removal or not. You need some nitrogen and phosphorus, which is normally present in wastewater in abundance anyway. So it's not something you have to worry about. Number 4 is the proper temperature. You want to make sure the temperature of the wastewater is where the bacteria best operate. In addition to that, there's a couple of physical parameters I like to think of them as that's important for operation too. In addition to temperature, we got pH and alkalinity. You need the right amount of that. You get too outside of those ranges and things can start working less efficient. Conductivity and is also similar to pH, where under most conditions it's fine, but if the conductivity gets too high, then you may have some issues, or too low. We'll talk about that. And then lastly, inhibitors. Obviously, any inhibitors that you release may be a concern as well. And we're going to talk about each one of these in more detail coming up. So when we think about substrate is the amount of carbon or food coming into the system. Clearly, with our pet low bacteria here, we want to make sure that they're fed and fed well. Well enough to where they perform the way we like them. And so one of the major criteria we want to look at when making certain that we are feeding our bacteria properly is what we call the food to microorganism ratio. That is effectively for every pound of bacteria that's present, you need to give a certain amount of pound of BOD to them to make certain that they can grow and do the transformations that we want them to do. So we want to quantify this and actually calculate this. And so we know how to quantify the loading based on one of the previous modules where we talked about loading calculation. We know how much food comes into the system. That's the BOD in concentration times the flow in million gallons per day times 8.34. That would tell us how much BOD in pounds per day that is loading to the system. But how do we quantify how many bacteria are actually present? How do we walk through that? We'll do through that the next steps. So the first thing we have to do is measure the biomass in the system. And so one of the first things that's a term that's really important to know about is mixed liquor. Mixed liquor is when primary effluent mixes with return activated sludge in the aeration basin. That becomes what we call mixed liquor. And so mixed liquor is, if we measure the total suspended solids portion of the total suspended solids in the aeration basin, that is our mixed liquor suspended solids. So that's one way to measure biomass. You can also do the volatile fraction, similar to the VSS we talked about in earlier modules. Looking at the mixed liquor volatile suspended solids is another way people will measure these. Once again, these methods are measured the exact same way that you measure TSS and VSS. It's just you're doing the TSS and VSS sample on the mixed liquor and the aeration basin is the way we quantify that. One important thing to note is if you're looking to quantify the mixed liquor suspended solids or the MLVSS, as the case may be, you want to collect the sample at the end of the aeration basin to be a good representative sample of the amount of bacteria that's in your system. So if we want to measure using the measurements, once again, we can use the mixed MLSS or the MLVSS. In this example, we're going to use the MLVSS, which is the volatile fraction of the mixed liquor suspended solids. And there's a good argument because it's the organic content being measured. That's a better approximation of the bacteria that's present in the system. So if you know the MLVSS concentration in the aeration basin, you can calculate the total pounds of bacteria in your system by multiplying the volume of the aeration basin in million gallons times the concentration of the bacteria, as we're quantifying it based on MLVSS, times 8.34. And that'll tell you the pounds of biomass. This is very similar to the BOD equation we had in the previous slide, except we're using the volume of the aeration basin in million gallons rather than million gallons per day. And we're using the mixed liquor volatile suspended solids in this example. We could use the MLSS and use that as our biomass number, but it's based upon your facility's preferred measurement tool there. So if we want to calculate the food to microorganism ratio, we can use this equation here to solve for it, which is just the BOD times the flow times 8.34 divided by the mixed liquor volatile suspended solids times the volume of the aeration basin times 8.34. Now, one thing to be considerate of is that if you're just measuring your inflow to your wastewater treatment plant, that if you're not measuring actually what's going into your aeration basin and you have primary clarifiers, those primary clarifiers can remove 25 to 40% of your BOD. So you want to be certain that you are measuring truly what's going into the aeration basin and not necessarily what is being measured just at the inflow to the treatment plant. So now we know how to measure the food to microorganism ratio. What is our target? So an ideal food to microorganism ratio of 0.25, 0.5 is standard for conventional activated sludge systems. Now, this number can vary based upon your treatment plant and different considerations, but largely this gives you a biomass that is just slightly starved. And through that, those starved organisms form a sticky protective layer that helps them form flocks and settle better. If your food microorganism ratio is too high, then those slime layers formed, you get these dispersed flocks, so you can have high effluent TSS concentrations. And what we mean by high is greater than 0.5. If you have low or less than zero point 0.2, then you have a much more starving population, which forms weak pin flocks. And then you can also get a lot of filaments forming because the bacteria are stretching out, trying to find as much food as they can. So having too low of a food to microorganism ratio is obviously less than ideal. What we're shooting for is right around 0.25, 0.5 food to microorganism ratio that gives you good, healthy flock most of the time and will give you good effluent TSS removal and performance for your system. So as we said, the ideal food to microorganism ratio that we're shooting for is between 0.25 and 0.5. But, let's say you have a situation in which you have a high food to microorganisms ratio. You do the analysis, you have greater than 0.5. What is the possible causes? Number one, maybe all of a sudden you have a high BOD slug coming from an industrial source. It's causing a high amount of BOD higher than what you expected. That is one potential way that could happen. Number two is maybe you had an inhibitory toxic compound that came into your system and killed off your biomass. You would obviously see a drop in your MLSS or MLVSS as a result of that. So those are the possible causes. So what would be the indicator to the operator that this is happening? Number one, besides dying off the bacteria, you'd see poor effluent BOD results and also poor settling of your sludge. The things that the operator can do is increase aeration. If there is a high BOD, you can then provide enough air to make sure that the bacteria can grow and chew on that and eventually bring down that BOD. Or number two, decrease the wasting rate to increase the biomass in your system because you're not removing them as much. And then your microorganism population will come up and that ratio will then come down. On the flip side, if you have a low food to microorganism ratio, possible causes is maybe a low seasonal flow in which you don't have a lot of food coming in, or a rain event in which you have a lot of dilute wastewater that's coming in due to rain. This biggest observation you would see is poor settling. If you had this situation, maybe some microscopic observations too could happen. The solution to this is decrease aeration if you're over aerating, maybe. And secondly, increase wasting at this point to bring down the microorganism population so it's a little bit more in balance with the amount of food that's coming in. So we're going to walk through an example of how to calculate a food to microorganism ratio. We have the equation up above that we've mentioned before. And in this example, the primary effluent is a flow of 1.5 million gallons per day. The BOD coming in is 180 milligrams per liter after the primary clarifiers. The aeration basin is zero point 0.5 million gallons, and the MLVSS is currently 2,200 milligrams per liter. So let's walk through this problem here. So our knowns are the BODs 180 milligrams per liter. The volume, the flow is 1.5 mgd. The MLVSS is 2,200 milligrams per liter, and the volume of the aeration basin is half an mgd. Now, because we have 8.34 at the top and the bottom of this equation, we can cancel each others out because it's effectively like 1 divided by 1 or 2 divided by 2. It's the same. Those can disappear, and we don't need to use that in our equation. Just to show you that that's typically what we're doing, but we can ignore those for this problem and for a lot of problems like this. And also, the interesting thing is the units also cancel out. So we just have a ratio is what the answer is for this, not anything else, just a ratio. So in this problem here, we've got 180 times 1.5 divided by 2,200 times 0.5, and that gives us food to microorganism ratio of 0.25. Once again, unitless. So we just talked about substrate. Now we're going to talk about oxygen. Oxygen allows the bacteria to breathe and provides them also mixing as well too, because the aeration system mixes and keeps all the bacteria in suspension here too. Now the oxygen can come either as dissolved oxygen as under aerobic conditions, or nitrate or nitrite under anoxic conditions. Either way, you need that source of oxygen from the grow. And once again, the aeration or mixing also provides keeping the bacteria in suspension as well too. So some common methods of aeration include diffuse aerators, where the aerators are at the bottom of a tank, and those can be the fine or coarse bubble diffusers, depending upon what your needs are. Mechanical aeration, which are like surface aerators, like propeller type aerators that sit at the surface and just beat the water. And through that mixing, you get a higher surface area to volume ratio, which then allows the oxygen to get into the water. And there are some situations which you have combination of both diffused air and mechanical aerators as well too. This is an example of a couple of different diffused aeration systems. So you can see here a good example of some coarse bubbles and fine bubble diffusers. You can see how this typically is laid out with this manifold here with a series of legs where the diffusers are all covering the bottom to provide aeration. And this shows you kind of what that looks like in operation. You want a very fine bubble. You do not want large bubbling cauldrons. If that's happening, then likely one of your diffusers are broken. You want a very fine bubbly mist on the surface, similar to what the picture shows in the bottom right there. This shows one example of a mechanical surface aeration type systems. As you can see, it's almost like an impeller that just sits there and beats the surface. And as you can see, through that mixing action, increases the surface area to volume ratio, which allows for air to get into the water as well. So how much oxygen is needed? That is a very important question. So as a general rule, you want to maintain a dissolved oxygen content in your aeration basins between 1 to 2 milligrams per liter in the aerobic zones, obviously. In the anoxic zones, you want to be less than 0.5, closer to 0.2 is really what you want, or non-detect if you can even get that. But you want to keep it low, you want to keep it 1 to 2 in the aerobic zones of your system here. There are some recent studies that suggest that low DO operation, in which you can have the dissolved oxygen content, right around 0.5 to less than 1, can be done to get some simultaneous nitrification and denitrification and BOD removal in your system. But that is a very specific operational design that needs to be worked through to make sure that your system can operate that way. So I would not recommend that without proper evaluation of your system to see how that works. Now, when we think about how much oxygen is required, there are some general rules of thumb. They're a little bit specific for your wastewater, but for BOD removal, typically you need to be require about 0.9 to 1.3 pounds of DO per pound of BOD that you need to treat. That's a typical rule of thumb. If you happen to have too low of a residual, you're not meeting that BOD demand, then you can get incomplete BOD breakdown and potentially BOD in your effluent. If it's too high, then you just have wasting oxygen and too high of energy costs. Now, for nitrification, you actually have a much higher oxygen demand. In this situation, you need 4.6 pounds of DO per pound of ammonia that's being treated by nitrification. If you have too low, you can get incomplete nitrification occurring, in which you maybe do not oxidize all of your ammonia, or you get a partial nitrification, which you produce a lot of nitrite, which is not ideal. If it's too high, you can potentially have high costs, and you can inhibit denitrification, as we're going to talk about in a little bit as well too. So, if you have too much dissolved oxygen, it can. This is how it can potentially impact your noxic zone performance. Imagine you have really high DO concentrations in this aerobic zone, like near 7 milligrams per liter. If that's the case, when you do the recycle, you're going to be bringing that oxygen to the noxic zone, and the bacteria in the noxic zone would much rather use oxygen than nitrate for the metabolism. So they would preferentially choose oxygen and leave the nitrate untreated. And so your denitrification would not occur. So making certain that you have a low amount of dissolved oxygen, not low, but 1 to 2 at the end of your aerobic zone is important to if you happen to have a nitrogen removal system similar to this to ensure that your nitrogen removal system works well. Another item that you need is nutrients. So biomass, just like us, needs their nutrients and their vitamins. And so typically we'll think about nitrogen and phosphorus are the key things that they need, in which the typical ratio that we need is for every 50 units of BOD, you need 5 units of nitrogen and 1 unit of phosphorus. Now, wastewater typically has this in abundance. So that is normally not a concern. You also need micronutrients. Iron, manganese, and various other metals that are present in wastewater are also important metals that are required for enzymes in the bacteria. So luckily, those are likely available in abundance as well too. So that's something you do not need to be concerned with. If you happen to have a very high industrial discharger to your system, though, that is strictly just high BOD without any nutrients, you can get into a nutrient imbalance in which you may need to supplement your system, but that is a very case specific situation which you'll need to evaluate. So now let's talk about pH and its impacts on the microbial populations in activated sludge systems. So bacteria, like all of us, have a certain optimal range they like to perform in, and pH for them is no different. Typically, when we think about heterotrophs and denitrifiers, the main organisms that do BOD, oxidation, and denitrification, they've got a relatively broad range of pHs that they can exist in, between as low as 6.5 to high as 8.5. You get beyond that, you potentially start getting some inhibition occurring there. Conversely, the nitrifying population is much more impacted by pH, and they like a little bit more on the basic side, from 7 to 8.9, 8.7 or so is where they like to be at. And outside that, they can be impacted. And we'll talk about that next. So in this graph shows on the y-axis how efficient the nitrifying bacteria are, up to 100% efficient, and at different pH ranges. As you can see here, right around 8.2 is like the sweet spot for nitrifying populations. They like to be in that range. You get a little bit too low, the efficiency drops off. Get a little bit too high, efficiency also drops off. Now, what this shows is they're about 50 to 45% efficient at the pH of 7. I've seen efficient systems operate down to really pushing at 6.5 pH and still be able to do complete nitrification. But the system has to be designed to account for that sort of lack of efficiency in terms of their growth characteristics. Obviously, as you go too high of a pH, 9, 10, then you can get drop off performance as well. But I typically do not see that as an issue with a lot of wastewater treatment plants. The lower pH, especially with nitrification and the fact that the nitrifiers do consume alkalinity and push the pH down, that's where you typically are more concerned with. So keeping that pH higher, maybe potentially adding buffering or additional alkalinity into your wastewater to account for that consumption of alkalinity from the nitrifiers is something you'd want to consider for your system operations to keep that pH more closer to, above 7 at least. Now, as I just alluded to, and we talked about before, the overall process of nitrification consumes alkalinity. If we actually look at the process from ammonia to nitrate, for every pound of ammonia oxidized, 7.1 pounds of alkalinity is consumed. So that consumption can reduce your pH in your system. On the benefit, though, if you do denitrification, that process, the process of going from nitrate to nitrogen gas, that actually produces alkalinity, about 3.6 pounds of alkalinity per pound of nitrate reduced. So if you look at a net between the two systems, if you have a nitrification and denitrification system, you only lose about 3.5 pounds of alkalinity. I've actually had some clients that requested a denitrification zone be put into their system, not only because of the fact that they can remove nitrogen, which was not even in their permit, but just so they can get some alkalinity buyback so they didn't have to add additional chemicals. So it is something to be considered in terms of your operation that if you potentially have some alkalinity concerns, one way to maybe overcome that is have your system include a denitrification noxic zone where you do denitrification to try to buy back some of the alkalinity rather than having to purchase chemicals to add in additional alkalinity to your wastewater. Also, similar to us and everything, temperature can be a impact as well on secondary treatment performance as well too. The speed of microbial reactions as temperature increases, typically you'll get a higher, faster reactivity. There obviously is an upper limit similar to us. Like each person's unique and each person's different. Some people like a little cooler weather, some people like hotter weather. But at some point, they get outside that range and their activity drops. And same thing with bacteria as well. That warmer temperature typically increases microbial growth, but as it gets too warm, then you start potentially impacting performance. One thing to note, specifically nitrifying populations are very much impacted by temperature as well, where they will drop off their efficiency. And there are certain limitations in terms of nitrifying populations. It depends on um, the system and how it's designed. But you get less than 10 degrees Celsius, nitrifying populations get really, really difficult to operate. And you get 5 to 7, and they can potentially shut down. So it's an important factor to consider for your system operations. As temperature drops, it also changes your gas transfer rate because as the temperature warms up, maximum amount of dissolved oxygen that the water can hold drops. So at this point, then as it warms up, then your residual DO in your system could lower as well too. So that's another thing to think about in terms of how temperature can impact your performance. And then lastly, we talked about this earlier, settling characteristics is too. As the settling velocity, as the temperature warms up, the water becomes less dense. And then as it cools, it becomes more dense. And as it gets cooler, that higher density can then limit in terms of how quickly things will settle in it because of the depending upon the density of your flock. But in addition, with warmer temperatures, you also do produce, you have better microbial growth, better yield for the bacteria, and that can then mess up your food microorganism ratio if you're not paying attention to your mixed liquor, spin solids concentration, your aeration system. So just another thing to consider there as well. And as you decrease your food microorganism ratio, that can impact your SVIs as well, which can then also impact settling. So obviously, you cannot control temperature. It is not something where in your wastewater treatment plant you are going to add heat or remove heat from your main wastewater flow. That is not something that can be done. But as an operator, there are certain things that you can do to adjust for it. So with increasing temperatures, some of the things that the operator observation should see with increasing temperature is a lower residual DO because once again, the gas transfer is less efficient because water cannot hold as much oxygen at higher temperatures. So it's something that you'll observe. Also, potentially lower FDM ratio because of the fact that the bacteria are growing faster and the yield is better for the bacteria. So they're producing more bacteria for every pound of food coming in. As a result of that, they can lower your FDM, which can then impact performance as well. So some of the things you can do is number one, increase aeration to overcome that minimization of the drop in efficiency of oxygen transfer. And number two, you can consider increasing wasting in response to increasing mixed liquor spin solids concentration to keep that FDM ratio right in the ideal spot, as we talked about before. Now, in terms of decreasing temperature that you observe, what you'll typically will see is high residual DOs because gas transfer is improved. And also you can maybe see higher FDM ratios because once again, in this situation, the bacteria are slower, so the yield is less as well too. So you'll get less bacteria for amount of food being consumed. So you could get a higher FDM ratio. So a couple of things that the operator can do is number one, decrease aeration, you can save some money as a result of that because the oxygen transfer is much more efficient. Secondly, you can also decrease the wasting rate in response to a slowing bacterial population that will keep your food to microorganism ratio in the more ideal spot as well too. But obviously, you want to pay attention to what your food coming in as well. Make sure that you're not overcompensating potentially. So now let's talk about conductivity and how conductivity impacts activated sludge system performance. Conductivity is a surrogate measurement of total dissolved solids. Total dissolved solids is a measurement of all the different ionic compounds dissolved in the water. All these different ions are present there, and the impact that that has on bacteria is very similar to what happens to us with atmospheric pressure. As we go up higher in elevation, like an airplane, our ears can pop because the pressure on the outside of our eardrums is modulating, changing. Similarly, this can also happen to bacteria. So, in the case where there's too many ions in the water, if there's a sudden change in the amount of ions where they're much higher, it can kind of apply that pressure to the bacteria, squish them, and make them unhappy. Conversely, if the conductivity all of a sudden decreases too little, similar to us going up in elevation, we can expand, and and balloons going up in elevation, they can kind of expand and potentially pop, as the case might be. So as we start looking at groundwater that is higher in total dissolved solids over time, which then becomes the wastewater that has higher total dissolved solids concentration, or as the case may be with potential direct potable reuse in the future, or maybe total dissolved solids will build up as part of that. All of this could change your TDS and your conductivity of your wastewater, and just something to think about in terms of the performance of your system. Now, there are some studies that suggest that activated sludge systems can adapt to changing conductivity, but it takes some time for that adaptation to happen. So it's just something to think about in terms of your facility. Maybe there's actually some situations in which you have an industrial discharger that discharges a high or low conductivity wastewater that can all of a sudden mess things up. Just another factor to consider when looking at your wastewater treatment plan and what could make your activated sludge systems a little bit unhappy, as the case may be. Now, for the most part, conductivity should remain relatively constant in your system. That should be really just driven based upon your source water supply, like groundwater or drinking water, that really drives that conductivity. But if you happen to have severe I&I situations, which stormwater comes in, which will change the conductivity, or an industrial discharge that maybe has a high TDS discharge, those are things that could potentially impact your TDS for the short term in your system. And so those things are to consider. So maybe potentially have an equalization basin at the front end of your plant to be able to meter in these flows or to at least buffer some of these impacts might be a way to kind of keep the conductivity a little bit more stable and keep your bacteria population happy. So inhibition and toxicity. So as with everything, toxic compounds and inhibitory compounds can impact bacteria as well. And some of the more common sources of inhibitory compounds would be industrial wastewater, where potentially a industrial user may discharge some chemicals down the drain that they didn't realize its impact, including things like heavy metals, surfactants, pesticides, and cyanide. These things can um, potentially impact your system. And you would see this by potentially seeing poor effluent quality. Obviously, as the bacteria die off, you'd see the effluent quality be less in your system. And also maybe rapid changes in the residual DO because bacteria get killed off. All of a sudden, you don't have them consuming that oxygen. And so then you'll just have saturation of oxygen in your water column rather than it being consumed. So those are some indicators. So just, having a good, robust industrial pretreatment program, if you have a lot of industrial users, something to consider. Also, just one thing to note is nitrifiers are definitely highly sensitive. So if you happen to have an ammonia or total nitrogen limit for your system, being really responsive and watching the nitrifying population to make sure they're protected as well, because they are frequently the first population to go out in systems. So another important thing to think about. So we understand all these parameters and all these different things. So how frequently do you need to monitor these? What is the recommendation for this? And we don't have any hard and fast numbers for this. Obviously, what your permit requires is going to drive a lot of this, but there's other like operational monitoring that that should be considered in terms of trying to keep in front of issues before your permit begins exceeded. So we've got a list of generally recommended frequencies we'd have for testing things. Once again, each facility is different. And so I would consult and think about how your facility operates and your resources too. But this is not a kind of a baseline in terms of what we'd recommend in terms of the frequency of just monitoring things like your mixed liquor spin solids concentration, your food to microorganism ratio, and whatnot. So just something to think about. So in recap, there are multiple factors that can influence your system operation. So being mindful of them, tracking them, understanding how they can change your system and adjusting for them is what's going to keep your system a little bit more stable and a little bit happier as well throughout operation. Moving on now to biomass removal and recirculation. What we're talking about here is how you control your biomass. So we talked a lot about the aeration basin, what needs to be operated, and the parameters that are important for that. Once the solids and the biomass gets to the secondary clarifier, there's a whole process of return activated sludge and waste activated sludge that needs to be managed. And thinking about what are the considerations you need to have for ensuring good operation of your system is what we're going to cover in the next section. So, secondary clarification. This process is slightly different than what you'd have with primary clarification. Now, typically, your TSS removal is typically higher, right around 99% removal. The spent solids or the mixed liquor spent solids will sell slower than primary solids as well. So, you do need a larger tank and lower surface loading rates, as we're going to talk about. And then also the sludge is not compact as well. So, really tracking you know, how well settling performance is important as part of this. And we're going to go more into that in the next few sections. Similar to primary clarifiers, secondary clarifiers can be circular or rectangular. The majority of the ones I've seen in the field are circular, but I have seen a few rectangular ones as well. It really is based upon your site plan and site development and preferences and a whole bunch of other considerations. But the two important factors that are important for a clarifier design, no matter which configuration we're talking about, is surface loading rate or surface overflow rate and solids loading rate. So the surface loading rate or surface overflow rate, as we talked about last time, is kind of the rate of the upward velocity of water through the clarifier per clarifier surface area. So this is, as we talked about before, the flow in gallons divided by the surface area in square feet. And when we do that division, we get gallons per day per square foot. Now, one thing to note is that you do not want to include the RAS flow in this. You want to only include what the flow is coming into the aeration basin. That's what's going directly into the clarifier for this analysis, because that is ultimately a net removal because it comes in at the top and comes out at the bottom. That's not ultimately driving your upward velocity. We're mostly focusing on just the wastewater that is coming into the aeration basin as the kind of cue in this consideration here. Solids loading rate is a slightly new terminology, at least for this system, for secondary clarifiers, in which what you're looking at is the pounds of mixed liquor spent solids being loaded to the clarifier per surface area. So the way we calculate this is our mixed liquor spent solids concentration. In this case, we do consider the RAS flow because that is driving solids into the system. So it's a flow coming into the aeration basin plus the flow of the RAS times the mixed liquor spent solids times the 8.34 divided by the surface area of the clarifier. And we'll talk more about each of these in the next couple slides. So when we think about, what is the typical design parameters for each one of these? Under conventional activated sludge systems, the surface loading rate for secondary clarifiers is right around 600 to 800 gallons per day per square foot, whereas the solids loading rate is about 0.8 to 1.2 pounds per day per square foot. Now, if you happen to have an extended aeration system or like an oxidation ditch system, which you have a much lower F/M ratio, your loading rate is going to be less because the bacteria are a little bit more starved, and so the settling rate's not as good. So in this situation, we're looking for a surface loading rate of 200 to 400 gallons per day per square foot, a solids loading rate of 0.2 to 1 pounds per day per square foot. So in terms of performance monitoring for our secondary clarification and the ultimate handling of the solids and the biomass associated with activated sludge systems, there's a couple of key parameters that we want to look at. Number one is hydraulic retention time, similar to what we talked about with primary clarifiers. Solids retention time, which is a new terminology we're going to talk about, and it is extremely important in terms of your system operations. The RAS flow rate, the WAS flow rate, sludge volume index, and sludge blanket. We're going to talk about each one of these. So when you talk about hydraulic retention time and solids retention time, you think because they have retention time, they're the same thing. Well, there's some unique characteristics associated with this. Hydraulic residence time is simply the amount of time that a gallon of water spends in the system. So it's effectively, you have a 100-gallon tank, you've got a flow rate of 100 gallons per minute. The volume of 100 gallons is going to spend 1 minute in that tank and then flow out. It's just how much time it sits in there. That is important. You want to make sure there's enough retention time so that the bacteria can respond. So there's a certain minimum residence time you want to shoot for to make certain you have good degradation of your pollutants. So that is an important thing to consider. And if you do want to control that, that can be potentially controlled by an EQ basin or this EQ tank at the front end of your system, or just sizing the basin appropriately for ensuring that you have the right residence time. So, but that's what that is. The solids retention time is the amount of time that the biomass stays in the system. And because we have the return activated sludge system, that changes the residence time than what it would be different what the hydraulic retention time would be. And that is ultimately controlled by your sludge wasting rate, which we're going to be talking about in the next few slides. So with the hydraulic retention time, this is the average time the water stays in the system, as we mentioned before. Under a steady state condition, which most of our systems hopefully are steady state, the flow in equals the flow out. So that is, most of 99% of the time that's true. If you happen to have some flow restriction on the outlet, you can potentially have a situation in which you can get some flooding occurring, and the next thing you know, because of restrictions once again on the outlet, that can cause the tank to overtop, and then this is not the case, but clearly that's not a desirable situation. And I've never seen it where the flow in is less than what is coming out of the tank, and which the system would drain, other than if there's a blockage and all of a sudden the blockage is removed. Other than that, that's not the case. Most of the time, we're looking at a steady state situation, which the flow in equals the flow out. So similar to what we talked about with the primary clarifiers, the hydraulic retention time is the volume of water in the tank or in the reactor divided by the water flow. And so one example would be the reactor volume in gallons divided by the flow in gallons per minute. So let's walk through an example, hydraulic retention time calculation. So let's assume you have a reactor or a clarifier, something that's 5,000 gallons. And the flow into the reactor is 10 gallons per minute, and the flow out is 10. So we got steady state situation. What is the retention time within this reactor? Well, we take our equation, the volume of the reactor divided by the volume of the flow. The volume of the reactor is 5,000 gallons. The flow is 10 gallons per minute. Now, I want to take a second and talk about the units. I want to explain, because I think paying attention to units makes sure that you're solving for the right thing here. From a math perspective, this 5,000 divided by 10 gallons per minute is equivalent to 5,000 divided by 1 times 1 over 10. And when we do that, we have to flip the units so that the minutes now goes at the top and the gallons goes at the bottom. By doing this now, we've got the nice thing where the gallons units cancel each other out, because the top and the bottom, they go away, and all you're left with is minutes. And based upon this, now our hydraulic retention time is 1,000 divided by 10, which is 500 minutes or 8.3 hours. Okay, let's take our equation for hydraulic residence time, which is equal to the volume of the reactor divided by the flow. And in this case, our volume of reactor is 5,000 gallons. Our flow is 10 gallons per minute is what our flow rate is here. Now, one thing I want to kind of explain, because as I mentioned before, focusing on units is a good way to make certain that you are solving for the right thing. So from a math perspective, thinking about the units, this is equivalent to 5,000 times 1 minute per 10 gallons. So when you do the multiplication version of this, the minutes that's on the bottom of the gallons per minute goes at the top, or the numerator side of the fraction, and the gallon stays at the bottom. It's just kind of the basic math principle there. And the nice thing with this then is that the gallons cancel each other out. And so the only units left are minutes. So when we solve for this now, we take our 5,000 divided by 10, and the only units left are minutes. So we're left with 500 minutes or 8.33 hours. Now, a very important parameter, maybe one of the most important parameters for operating your activated sludge system, is the solids retention time. This is once again the average amount of time the biomass remains in the system. And the way this is calculated is you first look at how much solids you have in your system, kind of similar to the volume of the reactor we had with the HRT. And then you divide that by how quickly solids leave the system. And one thing to provide a point of reference is when we talk about the system, we're drawing a big box around both the aeration basin and the secondary clarifier. And so we look at how much solids is in the system, and then we divide it by how quickly solids are leaving the system. That can be leaving the system through the secondary effluent or through the WAS. Looking at the solids wasting rate, and once again, we're looking at the combination of the secondary effluent solids and the WAS solids. Well, each of these we can quantify by using our loading rate equation, which is the flow times the concentration times 8.34. So in the case of the secondary effluent, you take the flow of the wastewater treatment plant, the secondary effluent flow, times the concentration of TSS in the secondary effluent in milligrams per liter times 8.34. In terms of the WAS solids, in terms of how much you're wasting, that is the flow that you're wasting, the quantity that you're wasting, and that is in milligrams per liter. The concentration of the WAS, which is going to be different than your mixed liquor spin solids concentration and different than the secondary effluent. So it's how thick the sludge is coming out underneath the clarifier times 8.34. And that will tell you your total solids removal in pounds per day. So let's walk through an example in which we're trying to solve for this. So here we have the basic equation that we use. So for the solids inventory, we're looking at how much total biomass in the system. And this is very similar to what we did with the food to microorganism ratio, which you multiply the volume of the aeration tank times the mixed liquor suspended solids concentration. And you divide that by how quickly the solids are being removed from the system, just as we talked about in the previous slide. So in our example here, we have a reactor that is 3,000 milligrams per liter. The volume of the reactor is 100,000 gallons. The WAS flow is 0.01 million gallons per day. And the TSS of the WAS is 8,000 milligrams per liter. The secondary effluent flow is 1 million gallons, and the TSS leaving the secondary effluent is 20 milligrams per liter. So now let's walk through each of these parts and how much each of them are. So first, the solids inventory. We've got 3,000 milligrams per liter and a volume of 0.1 million gallons. 100,000 gallons is equal to a tenth of a million gallons, in the case is. For the solids wasting, the effluent flow is 1 mgd, the effluent TSS is 20 milligrams per liter, the WAS flow is 0.01 mgd, and the WAS TSS is 8,000 milligrams per liter. So now we take these two equations, the equation, and we apply what we know and put the equations in here. Now, one thing to note, because we have 8.34 on both the top and the bottom, they cancel each other out. So we can actually ignore that and not need to worry about multiplying by 8.34 and just use the numbers that are remaining on the screen here. When we do this, we walk through the equation and we get an answer of 3 days. So now let's talk a little bit about solids retention time versus mean cell residence time. Solids retention time only includes solids under aeration. So that's the bacteria in the aeration basin, not including those that are in the clarifier that have no food and no oxygen. So they're assumed to be dormant and not actually active in that state. In comparison, the mean cell residence time accounts for solids both in the aeration basin and the clarifier, in which the equation above, you include both the volume of the aeration basin and the volume of the clarifier. And this assumes that there are no solids intentionally held in the secondary clarifier, which you could potentially have an increase in terms of the amount of solids in there compared to what you would expect from the mixed liquor suspended solids. But we're going to ignore that. This equation ignores this at this point. But what's really important is to understanding what your system is designed for and make certain that you measure your performance based upon that design standard. Going back to the solids retention time, though, there's a couple rules of thumb that we have. For BOD removal, typically a 3 to 5 day retention time is all that's needed for a BOD removal to occur, to allow enough time for the heterotrophic bacteria to do complete BOD oxidation. So if your SRT is too low, you can have elevated effluent BOD. If it's too high, then you could have inefficient oxygenization, because then you have too much bacteria in there and just trying to get oxygen within that thicker wastewater. This thicker mixed liquor becomes less efficient. So that's one thing to think about. From a nitrification standpoint, it requires more time because these bacteria are slower and take longer time to be able to maintain their population. So as a result, typically you want to have between 8 to 20 days in terms of the required retention time for nitrification. If it's too low, you can have incomplete nitrification, and which can also then impact pH and then also produce nitrate as well too. If it's too high, solids retention time is too high, you're going to have inefficient oxygenization, as we talked about before, and potential poor settling sludge. The SRT, whatever you operate your SRT, should be established based upon the slowest growing target organism you're looking to keep. If you're only trying to do BOD removal, your retention time should be 3 to 5 days. But if you're looking for nitrification and continue those, you want to have between the 8 to 20 days, depending upon your system operation and design for that, and temperatures as well too. So when thinking about this, thinking what is your target and what you want to target, what is the main parameter that you can control that can help you maintain the SRT that you're shooting for? That is the WAS. You can't change, indirectly, you can change what the mixed liquor spin solids concentration is. You cannot change the volume of your reactor. And in theory, if your system's performing well, what is coming out the secondary effluent in terms of the solids removed from that is going to be pretty low. The main thing that you can control is your WAS flow rate and how much solids you actually remove from your system. So it is important to view that as your controlling lever, and then understand that it does have effects. The more you waste, that is going to drop your mixed liquor spin solids concentration. So you're going to have to not over adjust your WAS. You want to slowly adjust your WAS and see how your mixed liquor spin solids concentration will adjust to that, and then use those to fine tune to get to the SRT that is your target. So how do you determine what your WAS flow can be? Well, taking the equation we have up above, which is the standard SRT equation, if we shuffle around the formulas and solve for the flow of the WAS, you can use this equation here with your system to determine what your WAS flow rate should be here. So leave it here for your reference. Now, we talked about the WAS. Now let's talk about the RAS. The RAS has a very important role as well, too, because that is ultimately what's returning our biomass to the aeration basin to be active and to actually do what they need to do. So it's a very important function there. And the typical flow rate for the RAS is typically between 50 to 100% of your influent flow. I will say there are some facilities that have a set RAS flow rate. I highly recommend that you actually have an adjustable RAS flow rate that adjusts for the influent flow rate, for the simple reason that if you have a set flow rate and you happen to get a surge of water into your system, it can push all of your solids into your secondary clarifier, and it will take a long time for the solids to come back to the aeration basin. In the meantime, your aeration basin does not have enough solids to do proper treatment, and you can have incomplete treatment. So it's an important thing, if you do not have, to at least, if it's not automatic, at least as part of your operation, to consider adjusting the flow rate of your RAS based upon expected flow events and rainstorm events as well too. However, there is a way that you can calculate to determine what your target RAS flow rate that you're looking for in this case. So now we're going to walk through how you can calculate your RAS flow rate. This is ultimately a solids mass balance around the clarifier. This is the primary effluent flow times mixed liquor spin solids times 8.34. That is the loading of biomass to your secondary clarifier divided by the RAS concentration minus the mixed liquor suspended solids concentration times 8.34. Using this equation can give you a starting point in terms of what your RAS flow rate should be, and then adjust based upon performance. Another important parameter that you should check for operation of your system is what we call the sludge volume index. This is the volume of sludge that is occupied in a standard 1 liter column after 30 minutes of settling. This is kind of a measurement of how well settling your sludge is. And the sludge volume index is a value that is milliliters per gram. So it's milliliters of space taken up in the sludge volume by gram of biomass that's in that particular sample here. So if you look at the equation, you take the sludge volume, which is you put a mixed liquor into a standard 1 liter column, you mix it up and let it sit for 30 minutes. Then you determine what that sludge volume is after 30 minutes, that dark brown layer that roughly looks like 400 mLs on this graphic here. That sludge volume of 400 mLs in this example, divided by the mixed liquor suspended solids concentration in terms of milligrams per liter, times the unit conversion rate of 1 gram per 1,000 milligrams to get everything into grams at the bottom. That will tell you what your SVI number is. So in this example, in which we had initial mixed liquor suspended solids concentration of 3,000 milligrams per liter, and our sludge volume is 400 milliliters in 1 liter of total 1 liter in this example here, we take 400 divided by 3,000 times 1 over 1,000. In this situation, the liter units cancel out, the milligrams cancel out. We're left with milliliters of solids per gram of solids. And that works out to be 133 milliliters per gram. So for your system, what is your target? What do you really want your SVI to be? Well, if you have a really high SVI, which means a high volume per gram of mixed liquor, that means you have poor settling sludge. Typically, you have a higher effluent TSS. This typically is indicative of a younger sludge with a low SRT, typically. An ideal SVI is between 100 to 200 milliliters per gram. That would typically gives you high effluent quality. If you have a very low SVI, that suggests that we're talking about less than 80 milliliters per gram. Typically is associated with a high turbidity, really, is what you're having, and typically associated with an older sludge in this situation. So one of the ways that you can control your SVI is based upon the food to microorganism ratio, which then drives the type of organisms you have in your system. This graph here shows an idealized version in terms of how your food to microorganism ratio can impact the relative abundance of different organisms in your system here. And what you'll see is right in the middle in this graph, you have peak diversity in terms of different organisms in your system. And that is typically what you want to see. You want to see, obviously, your nitrifiers and your heterotrophic bacteria, but having some amoebas, some flagellates, some ciliates, and some rotifers is good. Once you start having too short of a sludge age, and which results in too high of an F to M, you can potentially then have much less diverse, in which you're mostly driven by ciliates, flagellates, and amoebas. So you don't have the ciliates, the stalk ciliates in your system or rotifers. But if the sludge age gets too long, then you'll get worms growing as well. And when you start seeing that, then you know your sludge age is getting too long, and it's not a healthy biomass. So the ideal is to have a really diverse community with an optimal diversity that does not include worms and too many rotifers in your system. Of course, this is somewhat driven based upon your system and the unique characteristics of your wastewater. So this is a general rule of thumb, but each system is a little different. So sludge blanket is also another very important parameter to think about. The sludge blanket is the depth of sludge in a secondary clarifier. That's how thick of settling, a thick of mat of sludge you have at the bottom of your clarifier. And this is ultimately controlled based upon your RAS rate for your system here. In smaller systems, you can sometimes use what's called sludge judge to measure the depth of that. Larger facilities may have automatic sensors that can do that, but a typical target is 1 to 3 feet is your typical target for a sludge blanket. Now, the sidewater depth is the amount of clear supernatant that is above the sludge blanket, and you typically want that between 13 to 16 feet. That gives you enough headspace so that in case a surge of water comes in, you will not flush out the bacteria, the biomass, into your effluent. And then lose biomass, then also exceed your TSS effluent limit. So pulling all together, for conventional activated systems, you need to know how the biomass transforms pollutants, what parameters influence the biomass health, troubleshooting and optimization strategies, and the different unit operations and flow paths for these systems. Besides monitoring your effluent to make sure that you meet your discharge limits, it's important to monitor different points inside your wastewater treatment plant to ensure that each unit operation is performing as it should. And then, if it's not, making appropriate changes as needed. That way, you can help prevent a future downstream effluent exceedance there. So, being mindful of your system operations and making a plan to adjust as needed is really important for your system. So, kind of give you a few examples of things we'd recommend. Obviously, for each facility, there's a lot of variability and potential other parameters to measure. But let's first look at solids retention time. Say you have a aeration basin in which you want to maintain an SRT between 6 to 10 days. Well, if your SRT is too low, you want to decrease your waste activated sludge flow rate. That way, you're keeping your bacteria in your system longer. They'll raise the SRT, then the bacteria will stay there longer, and that will get you within your target. Now, inversely, if SRT is too high, you want to increase your waste activated sludge flow, pull more bacteria out, and bring that sludge retention time down. For aeration basin, say you have an aeration basin which your target dissolved oxygen concentration is 1 to 2 milligrams per liter. And let's say you have a situation which your aeration concentration is lower than 1 to 2. First thing you want to do is look at the mechanical process of your system. Make sure your blowers are operating. Make certain that you don't have any leaks in your piping that's leading to your aeration basin. Look at the bubbles in your aeration basin if it is a fine bubble diffuser, and look to see if you got those fine bubbles, or if there's a big cauldron of air coming out. That suggests there's a break in the line. So that's an important thing to look at. If that's not the case, then look at the loading to your treatment plant. Look at the flows and the BOD loading coming to your facility, and see if maybe you're getting more BOD coming into your plant than what your facility is rated for. And the results, your aerators just can't keep up. They're just not built for that. And so at that point, then maybe you need to start looking at, is there a new industrial user discharging your facility that maybe you need to regulate, or maybe it's time to upgrade your facility. These are all things to consider. Now, if your aeration is too high and you're above that 1 to 2, well, you're just wasting energy at that point. So just reduce your aeration and save that energy cost. Lastly, if you look at your clarifier effluent, let's say your permit is less than 20 milligrams per liter and you're lower than that. Well, that's great. Good job. Move on. But if you're higher than that, maybe check your sludge volume index and see how well settling your sludge is. Check the sludge blanket depth. If it's too high, maybe it's causing a washout. And so you want to draw the sludge blanket down a little bit. Look at the organisms in your sample by looking at them under a microscope. If you happen to see a good diverse community, maybe things are looking well. But if you're starting to see less diverse and starting to see organisms that are not ideal for your activated sludge system, then maybe you look to make some modifications. And lastly, check your food to microorganism ratio. That is always a very important thing to evaluate, and then make appropriate adjustments. And with that, we conclude this content for treatment process number 3, secondary treatment. I want to thank you for your time, and on behalf of ADQ, thank you for listening to this video.